once more, solutions for the pendulum. X of t has this form, which can be reduced to this form, so that alpha cosine of omega t plus phi is, in general, a solution for the motion of the given pendulum. Omega is the square root of g over L, where L is the length of the pendulum, and once more this applies to a simple pendulum oscillating with an amplitude much less than its length. Now, let's just look at this solution. Let's just take x of t equal alpha cosine of omega t plus phi. Now, I'm not writing the subscript 1 on the alpha or the subscript 1 on the phi, because I'm simply isolating out the real part of this solution and asserting that this real part matches the behavior of the pendulum and can be made to match the behavior of the pendulum for any set of initial conditions. This function describes the x-coordinate of a point moving around a reference circle. And let's see if I can draw a half-decent circle. That's not a bad start. Let's put an x-axis here. I think I'm tilting things a little bit, but we'll try to live with this. Okay, now the radius of this circle is going to match the maximum value of this function. And the maximum value of this function occurs when the cosine takes its maximum value. The cosine of an omega t plus phi, where t is interpreted as time, omega t plus phi can then be any real number. T could be a positive or a negative time. So that the cosine is going to oscillate. It's going to have a maximum value of 1, a minimum value of negative 1, so that the x of t function will have a maximum value of alpha, a negative value of negative alpha. The radius of this circle, therefore, is going to be alpha, which makes the maximum value of x alpha, the minimum negative alpha, and of course, here's the line where x equals 0 at the center of our circle. Phi is interpreted as just an angle on the circular model, so let's just say that phi happens to be this angle. Then we can interpret the function alpha cosine of omega t plus phi as the x component of a point that starts here on the reference circle and moves with angular velocity omega about that circle. It's clear that if omega is positive, we'll be moving counterclockwise around the circle. Starting at this point, as we move around the circle, as we move from here to here, the x-coordinate will follow. And as we continue to move around the circle, the x-coordinate will continue to follow our motion around the circle, so that if we have points around the circle, we can project these points down to the x-axis and get the successive positions of our pendulum as it moves from its initial position over to its leftmost position and then returns back toward the right, eventually reaching its original position, continuing its cycle. So the x-coordinate starts here, goes to here, comes all the way back to here, and then back, and continues. Any pendulum of this description has an amplitude of motion, which we identify with alpha, and an initial phase, which we identify as our phi. And that initial phase is the angular position at t equals 0, the angular position of our reference point at the t equals 0 instant. And I'll make the statement that any pendulum and any clock implies values of alpha and phi. That is, the motion of any pendulum as measured with any clock will result in an amplitude and an initial phase. I'll also mention that the initial phase is determined by the initial position, but not just by the initial position. If the initial position of the pendulum is here at this x coordinate, then its phase could either be this angle, or if we wish, we could let the phase be this angle. And the difference between this phase and this phase is that if omega is positive, if we start with this phase, we start from this position moving to the left. If we start with this phase down here and omega is positive, then our pendulum will initially be moving to the right. And there's a big difference between a pendulum starts here moving to the left and so forth, and a pendulum starts here moving to the right.